the software, we got the hardware, and now it was up to us to do this kind of arrange everything and to start using it. Wei-Qiang has a really hard task, and from time to time an impossible task to do some evaluations and to prepare something that was running, properly running, and really resulting with meaningful data. He did tons of experiments, different conditions, and he will just show us what was that and how it was done in a very nice overview.
Thank you for the nice introduction. So now talk about online digestions using Immobilized monolithic reactors. So I just want to mention again about bottom-up proteomics. It's nowadays a very powerful technology to identify proteins. So it will start with samples, then it tracks proteins, and in this case here is secreted proteins, and they have done normally trypsin digestions to cleave the proteins into peptides, and then have to go through HPLC separation to simplify the complexity of samples, and then the MS will take in to do fragmentations, analysis, and then Immobilized to process and extract information. So my work is focused on this trypsin digestion part. So I just want to mention again why we do this, the reason of our project. So for clinical proteomics, for example, for in vitro fertilizations, so the fertilization happens and then the embryo is cultured for 2 days, and then normally a morphological scoring system will be applied to decide which embryo to transfer. And then the live birth rate is around 41% for patients younger than 35 years. And during the cell cultures, embryo cultures, there's secreted proteins in the mediums, and it's possible to do proteomics and assessment to hopefully improve the successful rate. But the normal traditional proteomics assessments will take very long, and it's not fit in here because this decision has to be made very fast. So this is our project. So we want to speed up the proteomics analysis. We have several parts. So my part is about the online digestion part. So just to detail about protein analysis. So the samples normally has to be treated for denaturation and aggregations. Normally use urea or other chemicals to denature proteins, and then use DTT to open up the disulfide bonds, and use other estimate, for example, to block the free cysteines. And then the protein digestion. For in solution ones, in our lab we use promethyltrypsin. It's actually a polytrypsin, and it was typically treated, and it was also methylated and licensed. And we only use 1 to 50 ratios, and the digestion was normally done at 8.5 pH and 37 degrees overnight. So it's, you can see here it needs more than 16 hours, so the whole analysis time is very long. And for online digestions, we use Immobilized enzyme reactors. Here we use sigma boron trypsins, and it was typically treated. And it takes minutes to do the digestions, and then the digested peptide directly go to the trap column. So the reason we use monolithic column is because it has many very good characteristics, including continuous porous materials and low meso pores and lower pH height, and can run very high flow rates, and also lower back pressures. Especially when we immobilize the trypsin on the monolithic columns, we can get a fast digestions, and we have a higher enzyme to substrate ratios, and then we have enhanced digestion efficiencies and have lower autolysis, and we can operate at higher pH and also higher temperature. just mention that pH is really important for the TRIPS digestions. This is some result we did at the beginning. So we try to do at pH 6 for digestions, and you can see here, this is the BSA. The undigested protein is still a lot here, and when we increase the pH to 7.5, you can see there's almost no undigested ones here. But we want to use similar pH as the in-solution ones, that is 8.5, but there's some difficulties because the separation column we are using is C18 reverse phase columns. The pH range is 2 to 8, so it's not good for the columns, so we have to come up with something. So we use post-under mixins, so we just use a simple TPs. So the digest solutions with high pH, pH 8.5, go through the RMS, then mixing with another pump with TFAs, then after mixing, we go to trap column with much lower pH. And also, so now we can use 8.5, and also it's possible that we can also use higher organic solutions. So after mixing, the organic solution will not interfere peptide trappings anymore. So here is a picture of our systems. As you can see here, we have two wash syringe pumps. This Hans already introduced. This is a box. We have two pumps here. And here is another box from also lab. This is a switch box. We have it's possible to have 10 switch wheels, but on this box now we have 6. And here is a small, white ones is a corn oven. We also from lab is a controller for the corn ovens. And in addition, we have auto samplers, and we have LC packets, nano pump, and also here's a loading pump, here's another nano pump, here's a UV. And inside this box will be the TRIPS RMS is like this, so it's a 100 microliter RMS. Here is our MS, it's a local Amazon SPDT. So here's the flow path of our systems. So first, here we have 2 nano columns. Normally we have 2 methods. For the first method, we first do digestions. So the sample will go through the RMS, TRIPS columns, and then mix with the loading pump, and then go here, go to the trap column 1, and then go to waste. So the digestion peptide will be trapped here. And then it will be switched. That's only the loading pump will go to the trap column to wash the trap column to do desortings. And at the same time, we can start to wash the RMS using a wash pump to wash it. I think the nano pump 1 will start to elute peptide from the trap columns, and then go to the nano column 1, and then go to UV, go to MS for measurements. And for the other part, so we can also do digestions and then trap it to trap column 2, and as the same as before, then do desorting on trap column 2, and then separation on trap column 2, nano column 2 to MS. So the peptide separations we use nano HPLC, we use 300 nanoliter per minute flow rate, and the column we are using is 25 centimeters, 80 columns, and we trap column 300 micrometer from millimeters, and we use a ternary gradient for separations. And the MS we used at the beginning, I was using thermal LTQ willows, and after 1 year we get a new one. We start to use this Amazon SPDPB, and we have both here a nano VSR source, and we measure top 10 precursors with MS2 CRD fragmentations, and then measure normally between this and the range. And for the database search, we use the mascot. So the word is now we also update to the latest version. And we normally search against Swiss protocol database, and so the species will depend on the samples. And the TRIPS will be at the enzymes. We have normally set maximum mean cleavage site 2. And the chart will be 1, 2, 3 possible, and these other peptide tolerance, current tolerance, and also we have this fixed modification because we introduced this during the sample preparations. And also there's also one modification considered. And also we use a 1% force discount rate to validate data. So here I show you data for the method of development. So first, we want to choose which salt we should use in the buffers. So we choose two salts, one is ammonia acetate, the other one is TR. So the reason we choose these two is they are both volatile, and compatible with MS. So here we use 100 millimolar salt, pH 8.5. Here we have mixing our 10 microliter per minute with 40 microliter per minute mixing. Then here I show you, so these two samples are 3 picomolar BSA proteins.